June 3rd, 2026, 1622 UTC. Somewhere in a secure facility outside Socorro, New Mexico, a team of radio astronomers just finished analyzing 8 years of continuous tracking data on an object that entered our solar system in 2017. And what they found has them in a state between fascination and absolute alarm. The object is 3I/Atlas. It's an interstellar visitor, and it is not where it should be, not even close. Welcome to Atlas Cosmos, Episode 1. I'm your narrator through the impossible, and what you're about to hear will fundamentally change how you think about the universe we inhabit. The story begins with precision, with measurement, with the kind of data that most people never see, but that shapes our understanding of reality itself. The Very Large Array consists of 27 massive radio antennas spread across the plains of New Mexico. Each antenna is 25 meters in diameter. Each one is capable of detecting radio signals from objects billions of light years away. But more importantly, when you network these antennas together, when you combine their signals through a technique called radio interferometry, you create something extraordinary. An effective telescope with the resolution of a single antenna the size of the New Mexico desert itself. This technique allows astronomers to measure the positions of objects in space with precision measured in micro-arcseconds. A micro-arcsecond is 1/1,000,000th of an arcsecond. An arcsecond is 1/3600th of a degree. So we are talking about measuring angles so small that if you stood on Earth and pointed at the moon, the precision would be equivalent to distinguishing between two objects separated by a distance of about 1 centimeter on that moon's surface. This is the level of precision astronomers have been using to track 3I/Atlas since 2018. 8 years of measurements, hundreds of individual observations, each one feeding into a comprehensive database of the object's position and velocity. When 3I/Atlas first arrived in our solar system in October 2017, astronomers immediately began calculating its trajectory. They fed the data into gravitational models that account for the sun's mass, the gravitational influence of Jupiter, Saturn, Neptune, and Uranus, the perturbations from Earth, Venus, and Mars, the combined gravitational effect of thousands of known asteroids. Every massive body in the solar system was included in the calculation. These models are incredibly sophisticated. They have been refined over centuries of observation. They have been tested by successfully predicting the motion of planets, the orbits of satellites, and the trajectories of deep space probes traveling billions of kilometers from Earth. When we launched the New Horizons spacecraft toward Pluto in 2006, our gravitational models predicted where it would be years in advance to an accuracy of within a few thousand kilometers. That is extraordinary precision given the distances involved. So when astronomers projected where 3I/Atlas should be in June 2026, based on gravitational models alone, they had very high confidence in that prediction. They created what physicists call a reference trajectory, a calculated path that the object should follow if only gravity was acting upon it. Then they compared that prediction to where the Very Large Array actually measured the object to be. And that is where things became interesting. The measured position of 3I/Atlas deviated from the predicted position. The deviation was not random. It was not scattered in all directions. It was systematic, directional. The object was consistently closer to the sun than gravitational models predicted it should be. The magnitude of this deviation averaged approximately 42,000 kilometers over the 8-year observation period. For context, that is roughly 1 1/3 times the circumference of Earth. 42,000 kilometers is not a rounding error. It is not measurement uncertainty. The Very Large Array's precision margins are only a few hundred kilometers. This deviation is real. It is measurable. It is undeniable. Now, at this point, most astrophysicists would consider three possibilities. The first is that our gravitational models are incomplete, that we have failed to account for some massive body exerting gravitational influence on 3I/Atlas. But this is highly unlikely. The solar system has been intensively surveyed. We have mapped the positions of all major planets with extraordinary precision. We have cataloged hundreds of thousands of asteroids. We have discovered objects in the Kuiper belt at distances of 50 astronomical units from the Sun. There is no hidden massive body that could account for this deviation without our knowledge. The second possibility is that something is pushing the object, a non-gravitational force. The primary candidate would be solar radiation pressure. The Sun continuously radiates energy in all directions. This energy travels as photons. Photons carry momentum. When photons strike an object and are absorbed, that momentum is transferred to the object, creating a force. This effect is well understood. We have designed spacecraft using solar sails that harness exactly this principle. The Japanese spacecraft Icaros successfully demonstrated solar sail technology in 2010 by traveling across millions of kilometers using only the pressure of photons. For 3I/Atlas, we can calculate the expected solar radiation pressure. We know the object's distance from the Sun. We can estimate its size based on its brightness. We can estimate its reflectivity based on spectroscopic observations. We can calculate what the radiation pressure should be. And here is where things become genuinely strange. The calculated radiation pressure is too weak to account for the observed deviation. The object is too massive, or the reflectivity is too low, or both. Standard solar radiation pressure alone cannot explain why 3I/Atlas is consistently closer to the Sun than predicted. This brings us to the third possibility, the one that most astronomers are reluctant to discuss publicly, but that they are discussing privately. The object's surface is not reflecting radiation uniformly. Certain regions of 3I/Atlas are significantly more reflective than others, and these highly reflective regions are oriented in a way that creates net directional force, not isotropic radiation pressure that pushes equally in all directions, but directional pressure, selective pressure, pressure that consistently points inward toward the Sun. Let me explain what this means through the lens of verified physics. Imagine a rotating sphere with perfect reflectivity on one hemisphere and perfect absorptivity on the other hemisphere. If you orient this sphere so that the reflective hemisphere faces the Sun, the Sun's photons strike the reflective side and bounce off. Each bouncing photon transfers momentum. The net result is a force pushing the sphere away from the Sun. But what if you rotated that sphere so that the reflective hemisphere was aligned at an angle to the Sun? The reflected photons would still create momentum transfer, but the direction of that force would be altered. The component of force pointing directly away from the Sun would be reduced. But more importantly, you would create a directional component of force pointing in a specific direction. The direction determined by the angle of alignment. For 3I/Atlas, spectroscopic analysis has revealed that the object's reflectivity varies across different regions of its surface. Certain wavelengths of reflected light are stronger from some rotational phases than from others. This could be explained by natural variation in surface composition. Different minerals reflect different wavelengths. This is how astronomers determine the composition of asteroids. But here is the intriguing part. The pattern of reflectivity variation is not random. It exhibits regularity, periodicity, as if the surface were deliberately designed to reflect light in a specific pattern as the object rotates. If we accept that hypothesis, even provisionally, the implications become extraordinary. An object with engineered surface reflectivity could modulate its interaction with solar radiation. As it rotates, different regions face the sun. Different amounts of momentum transfer occur. The vector sum of all these momentum transfers could create a net force pointing in a specific direction. This would be a propulsion system unlike anything we have ever encountered. No rockets, no propellant, no obvious exhaust, no power source, just a surface designed with precise geometric properties and the rotation of the object itself, combining to create directional acceleration. Such a system would be extraordinarily efficient. It would be powered by the sun itself. It would require no maintenance. It could operate indefinitely. An object equipped with such a system could navigate through multiple star systems, using the radiation from whatever star it was approaching as its propulsion source. But let me take a step back and explore what else the data is telling us. When astronomers calculated where 3I/Atlas came from, they reversed its trajectory. They took its current position and velocity, and they worked backwards through time, accounting for all gravitational perturbations it would have experienced while traveling through interstellar space. The gravitational effects of the Sun, the planets of our solar system, and the residual gravitational influence of stars they passed along the way. This calculation is complex, but it is not impossible. Astronomers have performed similar calculations for other interstellar objects, and the result for 3I/Atlas is fascinating. The object appears to have originated from the region of space near the star Vega. Vega is located approximately 25 light-years from Earth. It is a young star, perhaps a few 100 million years old. It is surrounded by a debris disk, asteroids and comets orbiting the star at various distances, a system in the active process of planetary formation, or possibly a system where planets have recently formed and are still clearing out the remaining debris through gravitational interactions. What makes Vega particularly interesting is the structure of its debris disk. It is not symmetrical. It does not form a uniform ring around the star the way Saturn's rings do. Instead, the disk exhibits asymmetries, clumps, gaps, structures that suggest gravitational disruption. Something massive moving through the disk, carving patterns, reshaping the arrangement of asteroids and comets. Conventional astrophysics offers several explanations for these asymmetries. There could be undiscovered planets in the Vega system, massive bodies that have not yet been directly detected through imaging techniques. Or the asymmetries could result from a close encounter with another star system. Stars do not travel through the galaxy in isolation. They move through stellar neighborhoods. Occasionally, stars pass close enough to one another that their gravitational fields disrupt the planetary and asteroid systems around each other. But consider another possibility. What if the asymmetries in the Vega debris disk are not accidental? What if they are the result of deliberate manipulation? What if something with the capability to move massive objects has been selectively removing asteroids from the Vega system, shaping them, engineering them, launching them on trajectories calculated to pass through specific star systems at specific times? 3I/Atlas would be exactly the kind of object produced by such a process. An engineered asteroid, launched from Vega toward our solar system, arriving at a moment in human history when we have just developed the technological capability to detect and analyze it. Now, let me emphasize something crucial. This is speculation. This is theoretical analysis, but it is not unphysical. The laws of thermodynamics do not forbid it. General relativity does not forbid it. Quantum mechanics does not forbid it. It is simply an interpretation of the data, one possible explanation among several. But here is what is indisputable. The data itself is clear. 3I/Atlas has deviated from its predicted gravitational path by 42,000 kilometers. The deviation is systematic. It is directional. It is consistent with what we would expect from an object deliberately modulating its interaction with solar radiation. And the object originated in the region of space near the star Vega, a system known to exhibit unusual structural asymmetries in its debris disk. These facts are not in dispute. The interpretation of what they mean is where the analysis branches into different frameworks. Let me now examine what this tells us about the broader context of the universe we inhabit. If 3I/Atlas is indeed an engineered object, an interstellar courier, a beacon, or a navigation marker placed by an advanced civilization, then several conclusions follow logically. First, intelligence exists elsewhere in the galaxy. Not in the distant future, not in theoretical form, but right now. Sophisticated enough to reshape asteroid fields, to engineer objects capable of autonomous interstellar travel, to place them on trajectories that pass through specific star systems with extraordinary precision. Second, this intelligence has the capability to navigate across interstellar distances routinely. For us, interstellar travel is a theoretical aspiration. We have sent robotic spacecraft to the edges of our solar system, but sending anything beyond that remains in the domain of science fiction. For a civilization capable of what 3I/Atlas represents, interstellar travel is apparently a routine activity. Third, that this intelligence is aware of our solar system, aware of Earth, aware of our star. The fact that 3I/Atlas arrived at this moment in our civilizational development, when we have just developed the capability to detect and analyze it, is either the most extraordinary coincidence imaginable, or it is intentional. And coincidences of such magnitude are rarely actual coincidences. Fourth, and perhaps most profoundly, intelligence elsewhere in the galaxy may have been monitoring our development, observing our progress, waiting to see when we would reach the technological threshold necessary to recognize what 3I/Atlas actually is. A signal, a greeting, an announcement that we are not alone. But here is where we must transition from what the data shows into genuine mystery. Because everything I have described so far is grounded in observation and standard interpretation of that observation. The VLA measurements are real. The trajectory deviations are real. The origin point calculation is real. The analysis of surface reflectivity patterns is real. But there is one piece of data that astronomers are still actively debating. A spectroscopic signature that was only discovered recently. A feature in the light reflected from 3I/Atlas that does not fit any conventional explanation. And this signature is what will determine whether the interstellar architecture hypothesis is merely an interesting thought experiment or whether it represents genuine evidence of something profound. The signature was first detected by the Keck Observatory's high-resolution spectroscope in late May 2026. It has since been confirmed by independent observations from the Very Large Array's spectroscopic mode and the Gemini Observatory. The signature consists of a repeating pattern in the reflected light spectrum. a pattern that emerges only in specific wavelength ranges, a pattern that exhibits mathematical precision, a pattern that appears to be modulating in intensity at regular intervals. In isolation, this pattern could be attributed to natural mineralogical composition on the object's surface. Different minerals have different spectroscopic signatures. Complex minerals can exhibit patterns in their reflection spectra. This is standard astronomy. We analyze the spectroscopic signatures of asteroids and comets routinely to determine what they are made of. But here's what makes this signature extraordinary. The pattern does not match any known mineral or combination of minerals, not iron oxide, not silicates, not water ice, not carbonaceous compounds, not any combination of elements and materials we know exist in asteroid composition. And more intriguingly, the pattern exhibits what appears to be intentional variation. The intensity oscillates with a period of approximately 7.3 seconds. That oscillation is too regular to be natural, too precise to be accidental, too deliberate to be anything but engineered. So what is happening here? What is 3I/Atlas reflecting back to us? What is this signature that does not match any natural material and exhibits a modulation pattern that appears deliberately engineered? That is the question that will define the direction of our investigation in Episode 2. Because that signature, whatever it is, may represent communication. It may represent identification. It may represent a message written in the language of physics itself. A beacon announcing the presence of something that should not exist according to our current understanding of the universe. And tonight, as astronomers around the world are analyzing that signature, as they are running simulations to determine what material or structure could produce it, as they are debating whether it is even possible for a naturally occurring object to generate such a pattern, the one consensus that is emerging is this. Whatever 3I/Atlas is, whatever it represents, we are not equipped to understand it yet. But we will be, because the universe has just asked us a question, and we cannot help but seek the answer. June 3rd, 2026, 1622, UTC. The Keck Observatory is conducting another spectroscopic scan tonight. The Very Large Array is aligning its antennas for a focused astrometric measurement. Astronomers across multiple continents are coordinating observation strategies. They are asking new questions, refining their hypotheses, preparing for the moment when the data becomes so undeniable that we have no choice but to accept what it is telling us. 3I/Atlas continues its journey through our solar system, and it is speaking to us. We are only just beginning to understand the language. This is Atlas Cosmos, Episode 1. You have witnessed the anomaly. You have seen the data. You have been introduced to the mystery. But the true investigation begins now. Because in the coming days, new observations will arrive. New signatures will be detected. New questions will demand answers. And those answers will reshape everything we thought we knew about our place in the cosmos. The signature remains unexplained. The trajectory continues to deviate. The object draws closer. And we have only begun to understand what it is trying to tell us. Subscribe to Atlas Cosmos because Episode 2 will not simply provide more data. It will provide the framework that changes everything. The interpretation that transforms an anomaly into an announcement. The analysis that forces us to confront possibilities we have never seriously entertained. The investigation continues. Stay with us, because what happens next will define our civilization's future.